Hey, hello, great students once again. Thanks for watching so many of these videos. Geez, I think this is like I'm approaching 50 videos for this semester. Second semester here. It's crazy. It's too much. Should be a prize if you've watched all of them. I don't know what it would be. Consolation. Anyways, let's see. Let me point out two similar equations. They look in form very similar, which is interesting because they don't have much to do with each other. But I guess that's a hint that this type of connection or pattern occurs several times throughout chemistry and physics, I suppose. A mathematical relationship that helps us understand some connections. Way back long ago in chapter 12 or 13, I don't remember, on the chapter on kinetics, we said the rate of a reaction can be described by some constant k times the concentrations to whatever power, first order, second order. We should go back and review that before the final exam, right? But in any case, there's no mention of temperature, so the deal is this constant right here increases with temperature, or usually increases with increasing temperature. And the relationship between the rate constant and the temperature is given by the Arrhenius equation right here. This is its famous form, although it's hard sometimes to find what that constant A is, so we might rearrange that in a minute to make it more convenient so that we don't have to actually know what the value of A is. But you might recognize the form of this equation as y equals mx plus b, or in other words, the y-axis, the x-axis, the slope of the line, and the intercept right there. So yeah, it's a way to linearize the data, or to say, let's look at a connection between the Kelvin temperature and the rate constant. And it's perhaps most easily understood in linear form like that. And this is the important bit right here. The slope of that line, when I graph the rate constant, the natural log of the rate constant versus the reciprocal of the Kelvin temperature, when I do that, the slope of the line is equal to the activation energy divided by the gas constant in energy units. Interesting. That's one of the first ways we had to calculate theoretically the activation energy for a reaction. Whereas before this point, before the point we introduced this, we had no idea how to theoretically find the activation energy for a reaction. So, for example, if I had a slope of 13,000, it's a little bit tricky to define the units on the slope, but I know there's a Kelvin in there somewhere, and you could argue for something additional as well, but for now I'm just going to say it works out, believe me. The activation energy is therefore the negative of the slope. The negative comes from right there and or right there and or right there, times the gas constant. And if I had 13,000, the gas constant in energy units 8.31 joules per mole Kelvin, and my activation energy comes out to about 108,000 kilojoules to 3 sig figs at least. Interesting. So what if we wanted to use the 108,000 right here in what I call the 2-point form of the Arrhenius equation? It's useful because we eliminated the need to know that constant A, depending on collisions and orientations and probabilities and stuff like that. But here I have the rate constant 2 and the temperature 2 and the rate constant 1 and the temperature 1 and the activation energy. So what if I imagine that rate activation energy to be this? Then I should be able to solve for any of the others if I knew 1, 2, 3, 4. If I knew 3 of the other 4 variables, then I should be able to pretty easily, fairly handily, decide what the other unknown might be. So for any 2 points, point 1 and point 2, with on this line, which are described by this, as long as I have 2 points or 2 temperatures and 2 corresponding rate constants, as long as I imagine, trust, believe the Arrhenius equation is true, then I can just use those 2 points to find the, well, I can use one point to find the other, or I can use the activation energy. I can use the 2 points to find the activation energy, or I can use the activation energy to find one of the unknown temperatures or unknown constants. And for example, what if I had a rate constant of 0.112 at a temperature of room temperature, close to room temperature, 300 Kelvin, but I warm it up about 10 degrees, and I'm wondering what my new rate constant would be. So it doesn't matter which one you call K1 and K2, T1 and T2, as long as you are consistent. So my second temperature and my second rate constant. So this one might be the unknown one. This one might be the known. That would go with the 300 Kelvin, the gas constant in energy units, activation energy, and my warmer temperature. And then I just use my massive algebra skills and solve this baby. Can't solve anything here because I don't know that constant. This one divided by this one, this reciprocal, subtract that reciprocal, and to get rid of the natural logarithm, remember you take e to the x on this side and e to the x on this side, 1.397. Yep, and 4.04, multiply both sides by 0.112, and it seems like my constant has increased, not surprising. It used to be 0.112, warm it up 10 degrees, my constant grows larger. Interesting. Or if you just had 2 points or 3 points or 4 points, but let me pick any of these 2 points and go ahead and fit it in here. Let's see. What if I put oh geez, I don't know. Yeah, but in this case I put this blue temperature and constant up for number 2 here and here. Doesn't matter which one you call 1, which one you call 2. I think I put the 318. Yeah, I'll put the 318 here and the 0.0005 here. Oops, other way. 318 Kelvin temperature, 0.0005 here, and solve for the activation energy. So it's kind of a new, different question. But as long as you know enough information, plug in the numbers to the equation, chug it out mathematically, and this one came out to 105 kilojoules. An activation energy of 100-ish kilojoules is not uncommon at all. That's around the right ballpark. Lower than that would be just an easier reaction to get going. Or here I took that same data, blue, purple, and green, and I took the reciprocal of Kelvin temperature. At least I hope I did. Yep, I did. And I took the natural log of those constants, and I put it on a graph where I actually sketched a graph out. I really imagined I did it. I didn't really do it. So you could try this one and this one, this one, this one, this one, this one. Any 2 points should allow it to work. I think on this one I found the slope via a graphing calculator. That's what I did. I took these points and put them on some kind of mechanical program that could help me figure it out. Here I got a activation energy of 103-ish kilojoules. That's compared to up here 105. So either way you look at it, pretty close. I guess that's another way of saying these 3 points fall in fairly straight alignment. Fairly good agreement between the slope between what I do. I think I did this one and this one up here. What did I do? I did the blue and the purple. Yeah, so the slope between here and here was 105 kilojoules, but between all three, linear regression of all three, a little bit different. Alright, and so what's up? What's the other equation? The other equation is called the Clausius-Clapeyron equation for the vapor pressure of a gas phase of a solute, doesn't have to be solute, of a liquid above its liquid sample. So here's liquid water, gaseous water, or pick any liquid and any vapor of that liquid above. Not too surprising, is it, that as I warm up my sample, oh yeah, by the way, do you remember what the vapor pressure, that I kind of hinted at the definition. The definition is, vapor pressure is the pressure of a gas above a sample of its liquid in a previously evacuated container. Interesting. So the vapor pressure of water up here is this, and we call it P-vap, the pressure of vaporization. And for water has a lot of interparticle forces, so it's hard to, it has a high vapor pressure in it. No, I'm sorry, wrong way. Water has a lot of interparticle forces. That has a low vapor pressure. It doesn't want to evaporate very much at all. So its curve of vapor pressure versus temperature is kind of slow to rise, compared to ether, which has a liquid that has very few interparticle forces and evaporates easily as it rises very quickly. This is 1 atmosphere pressure. When the vapor pressure equals the air pressure, that's when it boils. So boiling happens here and here and here, and ethanol and ether are much more easily. If I want to linearize this data, I do a similar trick mathematically. Oops, wrong way. I take the natural logarithm of something on the x-axis and the reciprocal of the temperature on the other axis. And lo and behold, no surprise, it linearizes each of them, but of course they all have a different slope. And interestingly, that slope is described by this right here. Now this was the activation energy, but now this is called the heat of vaporization. Similar, it's an energy amount, the gas constant, and that looks similar. This, we don't really care too much, that the y-intercept, we don't care too much about that. If we can avoid using it, we will, and we can. And the y-axis. So let me go back to the 2-point form of that. If I want to eliminate that constant, I think about 2 points, point 1 and point 2, temperature 1, pressure 1, vapor pressure 1, temperature 2, vapor pressure 2, and that all boils down to this. If I want to switch these backwards, T1, T2, T1, T2, this is how I had my first equation, but sometimes it's written like this. Just don't be tripped up. That negative goes into flipping that backwards if you want to write it like that. So how to use it? Well, duh, it's very similar to the other one. I almost insult your intelligence. Here are 4 points. You could do this trick with any of these 4 points. See if it all works out. I think I chose the 10, 890 and the 100, 1080. I think this is for like liquid metal of some kind. Liquid lithium of some kind. I don't even remember. I copied the data from another source. But here's how it would work, right? Same equation, very similar equation as before. I put P2 at 100 and its corresponding temperature right here. Yes, that's correct. Add 273 to change it to Kelvin. And 10 is the pressure, vapor pressure of this liquid corresponding to 890. And the thing I'm imagining I don't know is the heat of vaporization, the energy that would require to vaporize 1 mole of that liquid at that temperature. Again, use the math skills, natural log of 10, subtract that, divide by that, take the 2.3 divided by this 0.0000, they lose 0, small number, and voila, we have a vapor pressure, a heat of vaporization, the energy it requires to vaporize 1 mole of that sample. Oof, a lot of math, but I see the similarities in the equations. Thanks for watching, guys. See you in class.